You're here because you want to master ARENES with a University of Cambridge graduate. Let's begin. For ARENES, I want to emphasize again that for these organic chapters, we want to focus on the reagents and conditions that we have to memorize, the reaction mechanism involved with this particular functional group, as well as the reasonings behind the certain reactions that ARENES can go through as well. In this chapter, we are introduced to a new kind of organic compounds that involve benzene rings. These benzene rings give it that aromatic property. Some of the common arenes that you need to know are your benzoic acids, your benzaldehydes, and your phenol. Please take note of the naming as well. So just to recap from my intro to organic chem lecture, remember that benzene can undergo resonance. This is where the double bonds within the ring itself can all shift by one position either clockwise or anti-clockwise. And because of this, your benzene ring kind of lives in these two states equally. And therefore, your benzene ring is usually drawn with just a circle in the middle. This circle denotes the pi electron cloud. That is the common electron cloud that is shared because of this overlap of your p orbitals, as shown over here. Because of the p orbital alignment, your electrons within each of these p orbitals are able to be shared across one another, and therefore you usually get this pi electron cloud. This pi electron cloud is really important for arenes because it forms the fundamental basis for the reactions of the benzene ring itself. Now on to some nomenclature of your polysubstituted arenes. You don't really need to memorize this portion, but this is just a quick FYI that when you have polysubstituted arenes, sometimes we will use the words para, meta, or auto to denote the positionings of other substituents within the ring itself. Now on to the reactions of your arenes. The main mechanism for this chapter is electrophilic substitution. So how does this work? First, you have to generate an electrophile. And how do you generate this electrophile? Well, that would depend on the type of reaction that we have to go through. And you usually have to memorize this reaction that is used to generate the very strong electrophile. And then what's going to happen is in the second step, the electrons in the pi electron cloud are going to get attacked by the strong electrophile. Do take note that this is also a slow reaction. And then you will form an intermediate product. And do take note that this circle is cut into just being shared by the 5 carbons with the plus charge inside within the ring, because the plus charge is also shared amongst the 5 carbons as well. And the reason why the ring doesn't go all the way is because the electron in the 6th carbon over here is being given away to the electrophile. And in your third step, the electrons in the CH bond are going to be given away and donated back into the pi electron cloud. And because of that, the CH bond is broken and you'll form a H+. And you will also restore the benzene ring pi electron cloud over here. Do take note that this is also a fast step, mainly because the intermediate is quite unstable and the product is much more stable because aromaticity is restored. Now what are some examples of your electrophilic substitution reactions? We have nitration over here, where we will substitute one of the H's, this one, with a NO2. And the reagent and conditions are concentration HNO3 with concentration H2SO4 as a catalyst, temperature less than 55 degrees Celsius. And the reaction to create the strong electrophile for this reaction is over here, which is a reaction of nitric acid with sulfuric acid. And this will help to generate the NO2 plus strong electrophile. So do memorize this reaction in particular. And once again, I must emphasize, do memorize all the reagents and conditions. It will also help if you memorize the products or the side products of the reaction itself, because you do not really want to spend some time to try and balance the equation during the exam. Next up is halogenation. Now I can also add X into the benzene ring itself. So how that works is I will just use Cl2 or Br2 with a Lewis acid catalyst, which is very important for this reaction. So either AlX3 or FeX3 at room temperature and pressure. The strong electrophile is X plus, and how it is generated is that the X2, the halogen, is going to react with the Lewis acid catalyst first, and that's why this is very important. And this Lewis acid catalyst is going to form the strong electrophile, and the Lewis acid catalyst will also form this intermediate. Now this intermediate over here is also very important because it is what is used to extract the H plus later on in the third step of your reaction. I'm talking about the H plus over here. And for the next reaction, this is Friedel-Crafts alkylation. So you can actually add any R group into the benzene ring itself by using these reagents and conditions, either RCl or RBr with excess of the arene, and you must of course have a Lewis acid catalyst over here. So it can be either AlX3 or FeX3 at room temperature and pressure. And the strong electrophile that is generated, again, is the same. You'll use the Lewis acid catalyst to react with Rx, and then you'll form the intermediate that will be used in step 3, and the strong electrophile over here, which is R+. Other reactions that benzenes can go through are catalytic hydrogenation. So this is where I'm just reducing the benzene and removing all the double bonds. So I can do this with H2 gas, with either nickel or palladium or platinum catalyst, and by heating. I can also do side chain oxidation for my arenes. Now what side chain oxidation does is that if there's any R group that is tied to the benzene ring, I can oxidize, and under the reagents and conditions of KMnO4 and H2SO4 heat, I can form my benzoic acid. It doesn't matter how long the R group is, how many carbons there are, it's going to get oxidized and you will just form your benzoic acid. Do take note that your equation has to be balanced properly. So don't just take this equation blindly, and please balance properly during the exams or when you're applying it to any question. Now the observation from this test, of course, is purple KMnO4 decolorizing. And do take note that this reaction is very important because it often gets missed out by students, and it's often tested during the exam because of that. Of course, with this, there is an exception where if there is a carbon here that is a tertiary carbon, that means it's not bonded to any hydrogen, this side chain oxidation will not proceed. Again, this is a very commonly tested trap as well. Do take note that K2Cr2O7 is not a strong enough oxidizing agent, so you will need to use KMnO4 for this particular reaction because KMnO4 is a very strong oxidizing agent. Now on to the effect of your substituents on your electrophilic substitution. So when you have substituents on the arenes that are not involved in the reaction, because your benzene ring is the main part that is involved, these substituents can have an effect on the electrophilic substitution. For example, you can have activating groups. So these groups generally donate their electrons into the benzene ring itself. And because there are more electrons in your benzene ring, it's going to have a higher rate of electrophilic substitution because you will attract the electrophile much better. It's like putting your hand in a jar of honey and waving it in front of a beehive. The bees are definitely going to come and get it. So because we donate the electron density to the benzene ring, you're going to increase the availability of the pi electron cloud. And you also stabilize the intermediate by dispersing the positive charge, lowering the activation energy of the reaction. On the other hand, deactivating groups withdraw electron density from the benzene ring, and therefore it has the opposite effect, which is it decreases the availability of your pi electron cloud and also destabilizes the intermediate by less dispersing the positive charge. Now also do take note that different groups also affect the orientation of the incoming electrophile for your substitution. For this, you don't need to memorize it because everything is in the data booklet. Here I've attached a crop out of the data booklet, and how you would use it is that, let's say you have a certain group G over here that is the substituent. Now you can tell whether it's an activating group or a deactivating group by this middle row, and you can also tell the position of the electrophile attack based on the position of G. So for example, if it was an LQ group, then it will strongly favor the second position and the fourth position for your electrophile to attack. Also, by knowing whether the substituent is activating or deactivating, you can also tell the rate of the electrophilic substitution, and you can also see if you need stricter or stronger conditions for your reaction to occur or weaker conditions for your reaction to occur. So for example, if I have the alkyl group in the substituent G position, this will activate the benzene ring, and for reactions like your nitration, for example, you wouldn't need to have the temperature at around 55 degrees Celsius. You can actually have the reaction at 30 degrees Celsius. So that's all for arenes. Again, I must emphasize that you remember these three things. One is to memorize the reagents and conditions for the reactions for arenes. Two is to memorize how to draw the electrophilic substitution mechanism. And three, it is to understand the principles behind the reactions of arenes itself. Once you do that, do more practice and you'll definitely master arenes. If you like this content, be sure to hit the subscribe button so that you can get more frequent updates from this channel. And if you want to enroll in my online class, be sure to hit the link below so that you can book a free call with me and I can run through your past papers and go through any doubts and clarifications you require and show you why my class is the best fit for you. I'll see you in the next lesson.